Previous lesson, what we did was we went through the introductory aspect of linear transform, finding the null space or the kernel and the range of a linear transformation. Okay. In this lesson, we're going to pick a very, like I said, a straight up example with a definition of T, and find the null space and the range. Okay, so let's read it together. Let T such that R3 maps to R2. In our previous lesson, we say V maps to W. So here, this V that we are talking about is the vector space R3, and then W is R2. Okay. B, the linear transformation defined by, so this T here that takes R3 and give us R2 is defined to be, it picks any R3 vector which is defined as A1, A2, A3. Remember, any R3 vector is defined by 3 entries. Okay, so we have A1, A2, A3, picks it in R3, and then what does it do? It transforms it and give us this as an output. Right, what it does is it will transform this to A1 minus A2, then 2 times A3, which is it's a two-dimensional vector, right? So it takes an R3, does perform this operation on it, these operations, and give us an R2 or a vector in R2. Our job here is to find a null space and the range of T. Now remember, the definition of a null space is defined to be all the x we can pick in R3. Here R3 is our V, such that the T of that x is going to give us, or the transformation of that x is going to give us the 0 in R2, and here the 0 vector in R2 is 0, 0, 0, 0, right? So you need to understand what is happening in this part. Okay, so you need to have a very clear understanding of the vector spaces you are dealing with. Since I'm transforming from R3 to R2, I need to make sure that my 0 vector here is at 0, 0. Okay. So what does this mean? It means that I'm looking for any x which is equal to A1, A2, A3 in R3, such that the transformation of x, and that is equal to the transformation of A1, A2, A3. That should give me what is the transformation is defined to be A1 minus A2 to A3, and it should give me the 0 vector. So this is what I'm looking for. I'm looking for all the x's such that when I transform them, this will be the output, and this should give us, or the output that I have here should give us 0, 0. What it means is, for any arbitrary s I pick, I know this is how the x is defined in R3, and I know this is how the transformation will be. So I want to make sure that this transformation I have to A3 is equal to the 0 vector in R2. Right, and if you have two vectors being equal, what it means is that the components are the same. So I have A1 minus A2 being equal to 0. So first component equal first component, and then I will have that A1 is equal to A2. On the other hand, the second component should be the same as well. That means A3 is equal to 0. So that is the only thing we can find from this transformation. So it means that the x that should give us this case is when x is equal to A1, and A2 is equal to A1, so I'm going to have A1 again because of this side, right? A1 is equal to A2, and then A3 is 0. So when I have this kind of x in R3, remember this is part of R3 because this is a 3-dimensional vector. Okay, if I pick a vector in this case, the transformation of this x that we have, this new x, which is equal to that, is going to be A1 minus A2. So here the first component minus the second component, that's going to be A1 minus A1, and then 2 times the last component. So A1 minus A1 is 0, and then this one is 0. So it means indeed, if I pick a vector of this form in R3, the transformation will give me 0. Right? What it means is that the null space is equal to any vector of this form, A1, A1, or you can call them AA, because since they are the same, you can just replace them by any variable you want. A1, A1, comma 0 in R3, such that and then we know you can either choose not to even call it such that, because this is true, because for every vector you pick of this form, you're going to get 0. Now some other person can also say that A1, A1 oh sorry, I didn't finish with this. So such that a1 is a real number, because this can be any number at all, right? So some other person can say that this vector is the same as a1 out 1 1 0. So a1 can be any value, any real number. It can be 2, it can be 9, it can be 5, whatever you want to pick. Okay, so then it means it's a scalar. So if I pick any scalar multiple of 1 1 0, it should give me the null. It should belong to the null space. So somebody can say the null space is equal to the span. Remember, span is just scalar multiple of something. The span of the vector 1 1 0 belonging to R3. And in this case, you don't have to put a1 equals whatever. The span here means that any scalar multiple of this. Okay, I hope this makes sense to you. So that is the null space. An example you can pick is remember, if I pick a1 to be equal to, so here if I'm looking at it from this side, if I pick a1 to be equal to 1, then the vector x I'm looking for that belongs to the null space is going to be 1 times that's going to give me 1 1 0. And so the transformation of this x is going to be the transformation of the vector 1 1 0, and that is given by, if you go back to the definition, is the first component minus the second component, then 2 times the last component. So the first component minus the second component is 1 minus 1, that is 0. 2 times 0 is 0, and indeed this belongs to the null space. We can pick a1 to be equal to 3, and the vector x here will be equal to 3 times that. Okay, and that's going to be 3 3 0, and then the transformation of this 3 3 0 is going to be first component minus second component. That's going to be 3 minus 3 0, 2 times the last component, which is 0. So indeed this is the null space. Okay, now let's go to the range of this vector, this transformation. Remember, the transformation is given by a1 a2 a3. The transformation of that is giving us a1 minus a2 and then 2 times a3. So what does the transformation look like? Remember, so the range is equal to, the definition is the transformation of whatever you pick. I can call it just x, such that x belong to R3, right? And then x here is defined to be a1 a2 a3. And if you remember the definitions or what we said about our null space, we said a null space is a subset of the V, and here the vector V is R3. And you should remember, every element you pick in the null space is a 3-dimensional vector. Okay, so it means that indeed this null space is a subset of R3, and we know that the range is also supposed to be a subset of the W, which is R2, right? The W is our codomain, right? If you look at the transformation, so what we are looking at is what is the representation, or how does the transformed vector look like. The transformed vector is indeed in R2, so it's just a 2-dimension vector. Okay, what we are really interested in is to have a general representation of the whole range of the transformation. Okay, now notice that the R of t given by this, it means that if you remember, or if you can notice, this a1 minus a2 times and then 2 a3, this is a 2-dimension vector, so this is an element of R2, right? So what can I say? If I can say that, then it means that all the vectors in the range of t is a subset of, is an element in R2. It means that the range of t is a subset of R2. But we can say more about this. Okay, now let's look at any element we pick in R2. We know that every vector in that belongs to the range of t, because the range of t is transformed to be this. So the range of t is just the transformed vector. How does it look like? When you transform it, this is how it look like. when you pick any 3-dimension vector, you transform it, it look like this. Okay, and we know that this is a 2-dimension something, because this will simplify to a value, this will also simplify to a value, and we have just a 2-dimension vector. And we know that every 2-dimension vector belongs to R2, okay, at least in the real numbers. Okay, now want to look at how does any arbitrary R2 value or vector look like, so that we can have a general representation of our range of T. Okay, if I pick any arbitrary vector in R2, which is b1, b2, I want to claim that this value or this vector belongs to the transformation of X. So I want to say that b1, b2 belong to the transformation of this. It belongs to the transformed vectors. Okay, if I'm saying that this belongs to the transformed vector, then it means b1 comma b2 should take the form a1 minus a2 to a3. What does this mean? It means that every 2-dimensional vector can be written in terms of this, where a1, a2, a3 are coming from the 3-dimension. Okay, so if we can write this that case, then it means that the R2 is also a subset of, because if every element in R2 can be written as this, it means that R2 is a subset of the transform vectors or the range of T. And in that case, if the range of T is a subset of R2 and R2 is also a subset of range of T, then it means the range of T is R2. Right? That's what we want to find. Okay, so if that is the case, then it means that B2 should be equal to 2A3. So it means that for every 2-dimensional vector you pick, A3 can be written as B2 over 2. Now, the other hand, it means that B1 is equal to A1 minus A2, meaning that A1 is equal to B1 plus A2. So here A2 we don't have an expression for, so A2 can be any real number. Okay. So what does it mean? It means that if indeed, and this is true because every vector in R2, if you pick B1, B2, we can represent that as this case, as A1 minus A2 as the first element and 2A3 as the second element. And if that is the case, it means that R2 is also a subset of the range of T. So, sorry, it's a subset, not just an element. So it's a subset. Okay. So in vector proofs, if you know that the range of T is a subset of R2 and R2 is also a subset of the range of T, then what does it mean? It means that the range of T that we are actually after is equal to R2. This is a very special case. Remember, somebody may say that, oh, it's true because it's transforming every 2-dimensional vector to R2, so it means the range should be R2. No, it's not always the case. The range can be different from the codomain. Remember, this R2 you have here is just the codomain. You don't really know whether the range is the entire R2. There are examples that we can take and go through, and after that we'll realize that the range is different from the codomain or the R2. Okay, but here we are lucky that the range is the same thing as the R2. If you really want to be convinced that every vector in R2 can be written as this, like I have here, with A3 being that, and then A1, A2 being any number in A1, you can pick an arbitrary vector like, let's say, first let's find T of 1, 2, 3, right? Want to pick example and know that indeed every transform vector is a 2-dimensional vector, which is equal to, you're going to take the second component minus the first, so the first component minus the second component, that, and 2 times the third component. We are using the same definition, which is going to be negative 1, 6, and this is a 2-dimension vector. So indeed every element you pick in the transform vectors, or the T of something, is going to be R2. Now let me pick an arbitrary R2. Okay, suppose we didn't know that, so here A1 is going to be that, A2 is going to be this, and A3 is going to be 3. So suppose we didn't know that this vector transformed to give us negative 1, 6, and we know that this is an element in R2. We are claiming that this should be the same thing as a1 minus a2 to a3. That's what we're trying to say, with some arbitrary a3 arbitrary 3-dimension vector giving us a1, a2, a3. Okay, so what this means is that we know that a3 should be equal to b2 divided by 2, where b2 is here is 6. Okay, so it's going to be 6 divided by 2, and that is 3. So automatically we have our a3 to be 3. Okay, and we know that a1 should be equal to b1 plus a2, where a2 can be any number, right? So we can pick any number. So if I pick a2 to be equal to 2, then what is a1? A1 will be equal to what is b1? b1 is -1, right? Because this is b1 plus a2, which is 2, and that will give me 1. So it means this vector, indeed -1, 6, can be written as a1, which is 1, minus a2, which is 2, and then 2 times a3. And this is what we have, right? So it means that every element you can pick from R2 can be written as the transformed vector, or is a part of the transform vectors, or T of x, right? So it means that the range of T that we are after is just R2. In our next lesson, I'll pick another example, and then which will have that the range will be different from the codomain. All right, see you in our next lesson.